Welcome to the Bible and Science. This is Dave Prentice. I'm a retired public high school teacher, certified in all branches of science and math. I've also taught on the Bible and science for many years, both in the U.S. and on many overseas mission trips. This is episode 15 of the Bible and Science. We're continuing to discuss the heavens and the heavenly bodies and so forth. So our main focus today is going to be how big is the universe, and we will probably get into a little bit how persuasive is the case for a Big Bang. But remember, there's no limit on the length of this series, so we may keep going. Previously, I talked a bit about the developments of the ancient Greeks in astronomy. And so when we come to Aristarchus in about 310 to 230 BC, he said it made more sense for the Earth to orbit the sun, but he couldn't prove it. While Aristotle had said the Earth was the center of the universe, so anybody that contradicted Aristotle was going to be ignored. Ptolemy, who lived from about 100 to 170 AD, so this is a few centuries later, he constructed a very elaborate model of how each heavenly body moved on its own sphere. The model was accepted for over 1,200 years. It was complicated, but it did work. The math worked. Meanwhile, Arabian astronomers were not doing theoretical work, but they would catalog stars. They named and cataloged many stars in the Book of Fixed Stars. They didn't propose any new models for how the stars moved. And then the Catholic Church became the dominant political power in Europe. It adopted the ideas of Aristotle, a pagan philosopher, and if you disagreed with a pagan philosopher, you were in danger of being burned at the stake. It's like now we have bumper stickers that say, I believe it, God said it, I believe it, that settles it. Well, it's kind of like Aristotle said it, I believe it, and that settles it. Okay, so major leaps forward began to be made in the 1400s and 1500s. Nicholas Copernicus, he was a very religious man. He didn't actually become a priest, but he obtained a position in astronomy at the University of Bologna. He was expected to make astrological predictions for the people of the city. Remember, astronomy has to do with the motion of the stars and planets. Astrology has to do with their influence on your life. So I wouldn't imagine that Copernicus was too thrilled, but regardless, he did that. And meanwhile, he developed a model where the sun was at the center of the universe. We wouldn't say it's the center of the universe now, but it's certainly the center of the solar system. So the math in his model was much simpler than the geocentric model, where the Earth is the center, but he couldn't back it up with experimentation. There was no such thing as a telescope yet. So maybe he didn't want to get burned at the stake, so he didn't publish his work until shortly before his death. Tycho Brahe, in the late 1500s to 1601, he was another devout Christian. He was a very meticulous observer. He obtained permission from the King of Denmark to use a building as an observatory, and he would sit out there night after night after night after night, recording the positions of various heavenly bodies, in particular the planets. He believed the other planets orbited the sun, but the sun was orbiting the Earth. Telescopes had still not been invented, but he did design some equipment, I'll show you in a moment, to record the position of planets and stars with precision that would not be exceeded for a long, long time. So he spent years in his laboratory recording thousands of observations, but he didn't know what to do with all of the numbers. Tycho Brahe had, among other things, an interesting thing with a cousin one time. He got into a duel with a cousin, and he had part of his nose cut off. So for the rest of his life, he had to go sort of noseless, which I guess would allow him to sit in a tower for night after night after night without being bored. But yet he did get married and have children. So anyway, Tycho Brahe was a Danish astronomer who got permission from the King of Denmark to sit there and do observations night after night after night. So remember from your geometry that a circle is divided into 360 degrees. Each degree is 60 minutes. Each minute is 60 seconds. So Brahe did not have a telescope available because it wasn't invented until 7 years after his death. He invented some things himself. He used a brass azimuth quadrant, which is shown at the left. It was a very, very big thing. It was like 20 feet long. It allowed him to record the positions of the heavenly bodies to within 48 arc seconds, about 1/75th of a degree, which is 1/27,000th of a circle. So night after night, he would write down his measurements. Here's Mars, here's Venus, and eventually he had volume after volume after volume of data, and he didn't know what to do with it. So shortly before the end of his life, he hired a young mathematician named Johannes Kepler. Johannes Kepler was, I think, one of the most brilliant mathematicians of all times when you consider what he did with what was available to him. Graphs had not even been invented yet, but he came up with some amazing things. So Brahe hired Johannes Kepler to analyze the data he had recorded from Mars. And Kepler attributed his success to thinking God's thoughts after him. That's pretty cool. And he had to just use statistical analysis to the numbers because nobody had even invented graphs yet. He came up with 3 laws of planetary motion. So he was applying this statistical analysis to all of these numbers, and he recognized, oh, this is going to give me an equation. That would be the equation of an ellipse. And then he tried other sets of data, and oh yeah, they were all elliptical rather than circular. So the first law he discovered was that the orbits of the planets were elliptical in varying amounts. An ellipse is like a stretched out circle. It has 2 focal points. One of them was the sun. He didn't know what the other one was. Later on, people figured out, oh yes, that's the center of mass of the other planets. So his first law, if you look on the picture, you'll see that there are ovals, ellipses. Well, that's what he discovered first. And then his second law, he discovered that if he drew a line from the sun to the orbit of the planet at the beginning and end of a specified interval of time, say 30 days, 50 days, something, he found out that when he calculated the area inside of the curve, the area was going to be the same whether the object was close to the sun or far away. That is, if it's close to the sun, it's got to go faster. If it's farther from the sun, it's going to go slower. I don't know how he was able to come up with that. He just said he was thinking God's thoughts after him. Then his third law is incredibly useful to us. This has been over 400 years now. He compared the orbits of the planets and discovered that for any object, such as a planet, orbiting another object, such as the sun, the cube of the distance from the center is proportional to the square of the period. Could you have figured that out? I couldn't. So he came up with a constant of proportionality, and it depended on the central object, not the ones in orbit. So the third law applies to other central bodies besides the sun. This is how we know how high above the earth an object needs to be in order to go around in exactly 24 hours, a geosynchronous orbit, so you can watch your satellite TV. After 400 years, we still use Kepler's third law to plan the path of space probes. We sent a probe out to Pluto, and after something like 16 years in flight, we had to fire the engines for about 16 seconds to make a correction. That's pretty good math. And this is from 400 years ago. What a brilliant mathematician. He also was able to use his laws to calculate the relative distances from the planets to the sun. So he said the distance from the sun to Earth, don't know what it is, but it's 1 astronomical unit. And then he calculated Mercury, Venus, Earth, Mars, and was able to calculate the radius of their orbit in astronomical units. Still didn't know the absolute distance. So Galileo, he died a bit later. He was one of the first to experimentally demonstrate that Aristotle was wrong about heavier objects always falling faster. Aristotle, of course, was overlooking air resistance. In 1608, Galileo read a description of a new invention called the telescope by Lippershey. So Galileo just had a written description. He didn't have one to look at, but he said, "Oh, I can do better than that." So he made a better telescope. It was not yet powerful enough to show parallax in the stars, but it did reveal that the moon is not perfectly smooth. Instead, it's rough, it's uneven. He also discovered that the sun is not perfectly uniform, but has sunspots. I hope he didn't look through his telescope at the sun. You actually can use a telescope to project an image. I've done this in my physics classes. He also discovered that there were 4 moons in orbit around Jupiter that were visible through a telescope. He also discovered, boy, he discovered a lot of stuff. There were many more stars in the sky than previously thought. The Milky Way was not a cloud. If you look at it on a dark night, it just looks like a cloud. Now it turns out it's composed of vast numbers of discrete stars. He noticed that Venus goes through phases just like the moon does. We have the full moon, the quarter moon. Well, Venus has the full, the quarter, the half, and so forth. And Aristotle had said that the heavens are fixed and unchanging. Well, he was wrong. Galileo discovered that there were a number of comets passing through the solar system, so the heavens were changing. He also concluded that the Earth orbited the sun rather than the other way around, and he was able to give some math behind it. So, the poor old guys earlier, since they contradicted Aristotle, their work was thrown out. Galileo was able to show mathematically that it works much better if the Earth orbits the sun. Of course, he was contradicting Aristotle, and so church rulers forced him to renounce his ideas under the threat of death. And the story goes, I have no reason to doubt it, that after he said, okay, I recant, he muttered under his breath, but it does move. Well, Galileo was succeeded by an English guy, Isaac Newton. He's widely considered the greatest scientist of all time because he worked with experimentation and theory both. He actually wrote more on the subject of religion than on science. In 1665, he was studying at Trinity College near London when the bubonic plague hit. It began to spread, so he moved to his family's estate about 60 miles away. While he was there, he figured out the law of gravity, which is given by that equation. The force of gravity depends upon a gravitational constant times the mass of two objects divided by the distance squared. I'd have a hard time figuring that out, but Isaac Newton did figure that out. And the famous story about his apple falling on his head, no, he said he was sitting in the orchard and an apple fell in front of him, and he got to thinking, well, if I was in some other part of the world, it would have still fallen toward the center of the earth. Why? And he reasoned that there was a force, an attractive force, which is called gravity, that was pulling things down. So Newton also invented differential calculus. That's pretty complicated stuff, considering there's a plague going on around you. And one of his contemporaries, Leibniz, worked much more on integral calculus. Differential calculus, you're breaking down a complex shape into an infinite number of infinitely small pieces, while integral goes the other way. It adds together an infinite number of infinitely small pieces to see how much area you get. So others besides Newton thought that the sun was somehow pushing the planets. He said, no. It's not that they're being pushed. Gravity is pulling them into a curved path. And he was able to come up with Kepler's laws from a mathematical perspective using gravity as the reason for the behavior of the planets. He also discovered the first, second, and third laws of motion. He later invented a much more powerful telescope. It used a curved mirror instead of a lens to gather light. So this is still the basis of portable telescopes. It still didn't have the resolving power to show parallax in stars, but it was able to show it in the planets. Now, when you look at the law of gravity up above there, F sub g is equal to gmm and all of that, that's been modified a little bit. That has to do with things under what we would consider ordinary circumstances, but in an intense gravitational field, there's a slight modification, but still it's so close that for most purposes, that's the law of gravity. So how do we know how far away the stars are? This is by using something called parallax. I mentioned this in an earlier session. You hold up your thumb at arm's length in front of a light, blink your eyes, left, right, left, right. It looks like the thumb is jumping back and forth, or if you focus on the thumb, it looks like the light is jumping back and forth. That's parallax. It's the apparent change in angle due to things being at different distances. So it wasn't until the 1830s that telescopes finally became good enough, powerful enough to show parallax in the stars. Parallax, what is that? Well, a light year is how far light travels in a year. It's a little bit less than 6 trillion miles. And sometimes to describe interstellar distances, we use parallax seconds or parsecs, which is about 3.26 light years. Okay, you're memorizing all of this, right? Ready for a quiz later? A parallax second is 1/3600th of a degree, or about 1 over 1,296,000 of a circle. So the closest star, Proxima Centauri, it has a parallax of about 0.77 arc seconds. That's about 4.25 light years or 25 trillion miles. Only the most powerful telescopes can show a parallax that small. So past about 50 light years, which is 0.006 or 0.06 arc seconds, which is around 1/10 millionth of a circle, you just can't trust the measurements. So 50 light years is really about the distance you could use to detect something if you got the best telescopes in the world to detect how far away they are using parallax. And those like Aristotle that said the stars, all of the other things are orbiting the Earth, well, no, they would have to be going far faster than the speed of light to be orbiting the Earth. So forget that. So what you do is you look from the Earth past a star you're looking for the distance of and compare it to the background stars that are so far, they're as you might as well say they're infinitely far. So you note the position of the star, and then 6 months later, you come back and you note the position of the same star, and you see how much does it seem to have moved with respect to the background stars. So parallax is useful for maybe up to about 50 light years. Past that, now you can't do that. And using parallax and triangulation and Kepler's laws and so forth, ever since Kepler's time, we've been able to calculate relative distance in the solar system using the distance from the Earth to the Sun as a reference. That's 1 astronomical unit. But there were no tests to confirm those calculations. But finally, in the 1960s, so some of you, that's ancient history to me. Hey, I was a little kid. It was not until the 1960s that the technology finally existed to directly measure the distances. Radar was invented in the 1930s, around the time of World War II, and it gradually became more and more powerful. We could send out more and more powerful beams, pulses of radar. So by the early 1960s, we have made radar powerful enough to bounce off Venus and Mars. Can't do them past that. But also the moon and things like asteroids or something that's fairly close. We could use radar to bounce it off and see how long does it take for the signal to get there and back? Well, radar travels at the speed of light, which is a known quantity. And so we were able to use those measurements for those two planets along with Kepler's third law, plug those into Kepler's third law and determine the distance to this planet, to that planet, and then we were able to calculate the distances of the other planets as well. So it wasn't until I was a little kid that we were able to actually confirm how far away the planets really were. So has anybody ever noticed, this is criticized sometimes as an error in the Bible. Psalms 19:6 describes the motion of the sun, his going forth, that's the way King James said, we would say its going forth, is from the end of the heaven, and his circuits unto the end of it, and there's nothing hid from the heat thereof. People say, that's a mistake because the sun doesn't orbit the earth. It doesn't say the sun orbits the earth. Instead, it says that the sun is making a lengthy path, a lengthy circuit through the heavens. In 1965, scientists at Bell Labs, Penzias and Wilson, discovered the existence of cosmic microwave background in space. So we can examine its apparent wavelength in different directions. It relates to the Doppler shift. And they discovered that it furnishes a frame of reference through which the Earth and the Sun and the entire solar system are moving in a lengthy orbit throughout the Milky Way galaxy. Okay, guess what? The Sun is making a circuit through the heavens, just like the Bible said. Just a little quick practical astronomy thing for you. How do we know that the Earth's axis is tilted by about 23 degrees or so? Well, you can do this yourself if you're willing to go over the space of a year. You don't have to go every day, just every few days. You select a convenient spot to watch the sun set over the space of a year. Go on your back porch or something and pick a reference thing, a fence post, whatever. So using a compass, notice how far north or south of west the sun is setting every few days. And over the course of a year, you're going to see the sun set more and more toward the south until it stops, comes back, and moves toward the north, further and further. And finally, it reaches its maximum toward the north, and then it starts coming back down. So the farthest north and south depend on your latitude, but the difference in degrees is twice the tilt of the Earth's axis. There was an old song that was used by the slaves in the days of pre-Civil War days called Follow the Drinking Gourd. And it says, when the sun comes back and the first quail calls, follow the drinking gourd. The sun comes back. They were talking about exactly this thing. And then also, they would notice that the quail would migrate at certain times of year, and they wouldn't do it until it was safe to migrate. So when the sun comes back and the first quail calls, follow the drinking gourd. The drinking gourd was the Big Dipper. And you look for the North Star, and you would follow that along, and you would get to the Tombihi River. And there was an old man whose name was given as Pegfoot Joe, and he would take you the rest of the way. So the slaves were aware of this, and they took advantage of that fact. So why are there seasons? Well, at the end of June, we're farther away from the sun. And you say, well, wait, how come it's hotter then? It's because the sun's rays are most direct on the northern hemisphere. If you're in the southern hemisphere, no, it's the least direct, that's the coldest. But end of June, most direct rays, hotter, that's the summertime. And then you go a few months later, end of September, now you're going to get to where the sun's rays are even in both hemispheres, and the days and nights are equal. That brings you through the autumn equinox. And then in the end of December, we're closer to the sun, but the sun's rays are most indirect on the northern hemisphere. So this is when we have the shorter days and the winter solstice happens. Then when you come around 3 months later, the end of March, the sun's rays once again are going to be pretty much even in both hemispheres, and you'll get the spring equinox. So this repeats every year, and it's very predictable. That's how you can determine when it's time to plant your crops. So far, we've been talking about things inside the solar system. So relative distances inside the solar system, the size of the whole thing, and so forth, were calculated using basic geometry and some variations developed from that. So Kepler came up with his laws of planetary motion, and then, after radar was invented centuries later, it was bounced off nearby planets. Previously, we had known relative distances, but now we could determine absolute distances using the fact that radar travels at the speed of light. But radar is not strong enough to tell the distances to any but the closest bodies, the closest planets, perhaps Mars and Venus and the Moon and maybe some other things that are going between in the area of the Moon and the Earth and so forth. But we couldn't use radar. What we did, though, was plug it into Kepler's laws. And once we had determined the closest distances, then we were able to calculate the other distances to the sun and to the other planets. Those distances are then used to calculate other distances that are much farther away. The next session will go into some of these in detail to determine how we were able to calculate the distances to very far away objects like stars and so forth. So, of course, we use the basic geometry so far. The Earth's average distance, we use triangulation on it, we use parallax on it, and then a few nearby stars called main sequence, which we'll get into. We determine the distances by parallax, but then we look at their spectral class. What is that? We'll get into that later, to calculate their absolute brightness. And assuming our calculations are correct, we then apply those values to calibrate the distance of thousands of other stars that are called main sequence stars. Then we look for some stars that get brighter, dimmer, brighter, dimmer. Those are called Cepheid variable stars. They seem to be near some of the main sequence stars from right up above. And then we use those Cepheids. We assume that the relationship between their period and brightness is the same for all the Cepheids throughout the universe, which I don't think is a correct assumption. It's not a valid assumption. We'll get to it next time. And then we use those Cepheid variable stars to determine the distance to relatively close galaxies. Then we make another major assumption, assume the brightest stars in each galaxy have the same absolute brightness, and use those to calculate farther distances. And then once we've determined, according to our presuppositions, how far away certain galaxies are, we use redshift, and that's going to be what we talk about a lot next time, the redshifts of the galaxies.